वाह,
Hmm?
बटन को पेंसिल से दबा रहे शंकर, क्या खराब है पेंसिल।
I didn't know that. Sorry. Check. Check, check. We'll start in 2 minutes. Okay, let's get started with today's session. Welcome to this live interactive session on the course Fluid and Particle Mechanics offered on NPTEL by Professor Sumesh and Professor Baswaraj. I am Shankar. I'll be your teaching assistant. This live session happens every Monday from 6 o'clock to 8 o'clock. So please feel free to attend and ask your questions here. And yeah, this week we'll be doing questions from week 7, where we'll be solving all the practice questions, all the graded assignments and the ungraded assignments, followed by completing a few more questions that I have prepared, and we can do that together. So let's start with the first question. Certain type of particles of density 4000 kilogram per meter cube are settling under the force of gravity in an organic liquid, CCl4, that is carbon tetrachloride, which has a density of 1594 kilogram per meter cube. The viscosity of CCl4 is 1.03 centipoise, and you know that centipoise is 10 raised to minus 3 in kilogram per meter second. The diameter of the particles is 0.1 mm. The volume fraction of particles in CCl4 is 0.2. Assume Stokes settling and the exponent to be equal to 4.1. Calculate the free settling velocity. So it's just a very straightforward question where the particles are given, the density is given, and they have been told that is settling under the force of gravity. Stokes settling regime is given, and we just have to calculate the free settling velocity. And the terminal settling velocity or the free settling velocity is given by g dp square rho p minus rho by 18 mu, which is 9.81 times dp is 0.1 millimeter, which is 10 raised to minus 4 square times rho p minus rho divided by 18 mu is 1.03 into 10 raised to minus 3. I'll give you a minute to finish the calculation, and then I'll give the answer. So therefore, the answer will be 0.0127 is equal to, okay, never mind. Just keep it in SI units since there was in meters per second. So 0.0127 meter per second is the correct answer here. Okay, we'll move on to the next question. Calculate the hindered settling velocity. So hindered settling velocity is given by the is given by this equation where we take the terminal free settling velocity times epsilon power n. Here epsilon is the free space the given in here, and it is n is the exponent that is given here. Now what is given is the volume fraction of particles is 20. So epsilon here is a free space, therefore 1 minus epsilon is equal to 0.2. Therefore epsilon should be equal to 0.8. Therefore the free settling velocity is found to be 0.0127 meters per second. Therefore the hindered settling velocity will be equal to 0.0127 times 0.8 power 4.1. And in meters per second, I'll give you a minute to finish the calculation. You will get the answer as 0.0051 meters per second. Okay, let's move on to the next question. The pressure drop in a packed bed depends on the average velocity in the channel's V bar. Choose one or more statements from the following which are correct. V bar is proportional to the superficial or empty tower velocity. V bar is inversely proportional to the superficial or empty tower velocity. V bar is directly proportional to the porosity. V bar is inversely proportional to the porosity. And we know that this is multiple correct questions. We know that the average velocity in the channel V bar is given by the superficial velocity V bar, V naught bar by epsilon, and here epsilon refers to the porosity here. Therefore, the correct answer is V bar is proportional to the superficial empty tower velocity, and it is inversely proportional to the porosity. let's move on to the next question. Question number 4. If V bar S is the superficial or empty tower velocity, and V bar S is the superficial velocity, and V bar is the average velocity of the fluid moving through the packed bed, which of the following relation is correct? Or what can you say which is higher as compared to the other one? So we know that from here we just wrote down the equation where we, instead of V naught, we have Vs here. So the average velocity is given by the superficial velocity divided by the porosity, and the porosity will generally be less than 1. Therefore, it's not very much less than 1. It'll be less than 1. So yeah, therefore we can say that the average velocity will generally be greater than the superficial or empty tower velocity. Okay, let's move on to the next question, which is given by this problem over here. A packed bed is constructed by considering a cylindrical column of 400 centimeters square cross-sectional area, and filling it with solid spherical particles of density 2.5 gram per centimeter cube up to a height of 1 meter. The mass of solids in the bed is 50 kilogram and the diameter of the particles is 1 millimeter. First question is find the void age or the volume fraction occupied by the voids of the bed. How do we do this question? So let us consider epsilon to be our packing fraction. We need to find out the void edge, which is given by 1 minus, sorry, it's not package fraction, this packing fraction, 1 minus packing fraction. And how do we find the void edge is pretty straightforward. We just have to find the packing fraction, which is given by the volume occupied by the solids to the volume of the packed bed. And the volume occupied by the solids can be found out based on the mass that is given, 50 kilogram, and the density of the particles, just 2.5 gram per centimeter cube. From those two, we'll get the density of the solids times the mass or weight of solid. How do you find the volume of the packed bed? It is very straightforward, as the dimensions of the packed bed are given, which is area of cross section of the bed times to the height of the bed, which will give you the volume. Therefore, density of solids is 2.5. Let's write down what we know. So we know that the density of the solids is 2.5 gram per centimeter cube, which is 2500 kilogram per meter cube. The weight of solids is 50 kilograms. Oh, sorry, this is W by rho. And the area of the bed is 400 centimeter square, which is 0.04 meter squared. And the height of the bed is 1 meter. Therefore, we can substitute for epsilon, which is 50 by 2500 divided by 0.05 times, sorry, 0.04 times 1. And this will be equal to 0.5. Therefore, this 0.5 is the packing fraction, which is the defined as the volume of solids to the volume of packed bed. What we need is void edge, which is 1 minus epsilon, which is again the same value, 0.5. Okay, let's move on to question number 6, where we have to calculate the equivalent channel diameter. Now let's read the question first. Again, same part of the question is given here. Calculate the equivalent channel diameter for the flow of fluid through this packed bed. And for that we need to find out what the equation for equivalent channel diameter is. Okay, the answer is equivalent diameter formula. I was not able to find out here, but I think it's 2 by 3 phi s dp epsilon by 1 minus epsilon. And here, since these are solid spherical particles, we don't have to worry about phi s at all, because phi s will be equal to 1. And the the particles are of 1 millimeter, which is 1000 microns. Since the answer is asked in microns, epsilon is equal to 0.5. Therefore, the equivalent diameter will be equal to 2 by 3 times phi s times dp times epsilon by 1 minus epsilon, and which is 2 by 3 times 10 raised to 3, which is 666.67 microns, or 0.67 millimeters. Okay, let's go to question number 7, in which it is given that an aggregate consisting of particles of density rho p is settling in a liquid of density rho l. Assume the porosity of the aggregate to be epsilon, and the density of aggregate rho aggregate can be approximated as. Oh, I'm sorry, this question does not come here. And in fact, question number 7 starts from here. So we know that epsilon is the porosity here, and the porosity, the volume that is there in the porosity will be occupied by the liquid, and 1 minus epsilon will be occupied by the solid. Therefore, the density of the aggregate can be approximated by the volume fraction of solids times density of solid plus the volume fraction of a liquid times the density of liquid. So volume fraction of solid is 1 minus epsilon times rho p plus volume fraction of liquid is epsilon times rho l. Therefore, the correct answer is option C. Okay, let's move on to question number 8. If the terminal settling velocity of a particle is ut and that of an aggregate consisting of these particles is ut aggregate, which of the following statements is correct? Among ut and ut aggregate, which will be the which will settle faster. So we know that when you consider ut, you are taking the dp, And when you consider the UT aggregate, you are considering the aggregate diameter, which is much more than the other. You're also considering the uh, density of aggregates and the viscosity of the aggregate solution. Therefore, when you consider these things generally, no, not generally, definitely the aggregate settling velocity will be greater than the terminal settling velocity of a particle. Okay. Next, question number 9. The concept of fractal dimensions is widely used to characterize colloidal aggregates. For a three-dimensional aggregate, which of the following is true? So let me first describe what is meant by this fractal dimensions. Obviously, this is not a huge part of your syllabus, but something that I found really interesting. So we know that there are one-dimensional, two dimensions, three dimensions, etc. But what is actually meant by 1.4 dimension? What is 2.7 dimension? These also exist, and these are known as fractal dimensions. We know that the 0th dimension is in fact a point, so we don't want to read anything like that. But if we have the first dimension, which is in fact a line, now let us consider a line that has of this. If we split the line into two parts of equal length, we'll get two line segments, each of L by 2. Similarly, if we split it into three parts, we'll get we get three equal segments of length L by 3, where L is the length of the main line. So what we can say here is that if the scaling factor is given by S here in the first step, when I convert it from a single line to two lines, is 2. The new number of lines that are found is 2. Similarly, the scaling factor here is 3. The number of lines formed here is 3. Now suppose I have a two-dimensional object which is plane, or which something that occupies an area. We know that a one-dimensional quantity does not occupy an area, but a two-dimensional plane occupies an area. Excuse me. So we have, let's take the example of a square. If I cut each dimension in the square into two equal halves, I'll end up with 4 squares. Similarly, if I cut each dimension of this square into three equal parts, I'll get 9 squares. Right. So if my scaling factor here is 2, the number of units that I get is 4. Similarly, if my scaling factor is 3, the number of pieces that I get is 9. Therefore, from these two we can see that there is some kind of relation that can be formed based on this. Now let us also discuss what happens in the 3-dimension, which characterized by the volume, and it can be any object. So the 2-dimension up to the second dimension, there we don't talk about the volume, but when the third dimension comes, we talk about the volume. Let us now consider a cuboid or a cube. And let us now consider, I am now cutting each line segment into two equal parts. I'll end up with, if you can imagine, I'll end up with 1 second. So I'll similarly have one over here, one over here, and one over here in the front. So what I'll end up with is, if my scaling factor is 2, I'll end up with 8 pieces. So if n is equal to 2, sorry, if the scaling factor given by s is equal to 2, the number of pieces that I get would be 8. Similarly, if I take the cuboid of length L or cube of length L, and if I did each length by 3 equal pieces, what I'm going to end up is with if the scaling factor is 3, what I'm going to end up is with 27 pieces. Therefore, if I construct a table which holds these data, where I use the line, and if the scaling factor is given here, number is given here, I'm gonna write down the dimensionality on the next one. Okay, if the scaling factor is 2, is that so that for a line, if the scaling factor is 2, the number of pieces is 2. If the scaling factor is 3, the number of pieces is 3. Therefore, if we write down this relation, and for a plane, we know that if the scaling factor is 2, we get 4 pieces. With the scaling factor of 3, we get 9 pieces. If we consider the third dimension, if the scaling factor is 2, we get 8 pieces. If the scaling factor is 3, we get 27 pieces. Now, if we can define the dimensionality of an object as D, which can be said as, so basically we see that it has a relationship where the number of pieces formed is equal to the scaling factor power the dimensionality D. Here D is the dimensionality of the object. Therefore, we see that the value D can be rearranged and written as, if we take log on both sides, we can say that log of n is equal to log of s power d, which is d log s. Therefore, we can write the dimensionality of any object as log n by log s, or we can write this as log of n to the base s. Therefore, if we write in that form, we'll see that the log of 2 to the divided by log of 2 is 1, log of 3 to divided by log of 3 is 1, log 4 to the base 2 is 2, similarly log 9 to the base 3 is also 2. But here log 8 to the base 2 is in fact 3, and log 27 to the base 3 is 3. And this is how the concept of dimensionality comes in. Now, what happens in the case of fractal dimensions? Let me first take a line and split this into 3 equal parts. And now what I do is I remove the so one second, I'm just trying to draw a neat figure. So we know that each of these line segments is L by 3. There's nothing new here, this is what was discussed. But now what I do is I remove the center line the center part of this line, and I add two more lines of equal length, that is L by 3. So what I have done is I have scaled it as 3. The number of pieces that are formed is 4. Now I can do this again and again and again. So in the next iteration, I'll get something like this. Again, if I do it, I'll get something like this. Sorry, here there will be one. It will be very, very complex to even think about right now. So yeah, you will get a very, very weird shape. And you will get a very, very complex shape such as this. Yeah, something of this sort is what you will get. And you can do this again and again and again, and it will lead to something known as a Koch curve. And the dimensionality of this Koch curve is given by log 4 to the base 3, which is approximately 1.4. I'm just fine tuning the value of log 4 to the base 3. Sorry, it's not 1.4, it is 1.262. Now what this means is that if you take a one-dimensional object and perform this kind of experiment, you are incorporating some kind of area into a one-dimensional object. You see, this although does not occupy a closed area, if you do it infinite times, we can actually be able to close this the one-dimensional line. So a series of lines have been represented like this as a dimensionality of 1.26. That means there is some two-dimensional characteristic that has come up as a result of this. Now let us do this for the two-dimensional case where I have a triangle. We take the case of a triangle, and what I now do is I mark the midpoints. Let's take an equilateral triangle for simplicity. I mark the midpoint of each line and I join the midpoints of each line. Now if we use a scaling factor of 2, we'll get 4 pieces. So that is fine. But what if we remove the center part of this? That means whatever is shaded in black or whatever the shaded is removed now. Therefore, my scaling factor is 2. The number of pieces I get is 3. Similarly, if I continue this, what I'm going to get is I'll be removing a piece from here, a piece from here, a piece from here. And yes, these needs to be removed. And if I repeat this, I'll again have to remove a piece here, 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 everywhere, wherever I have not done. Yeah, and all these pieces will be removed. So what I'm getting is every time I do this, I am incorporating some so the dimensionality that I get out of this is log of 3 to the base 2, which comes out to be 1.585. So what happens here is each time I do this setup, I'll be incorporating some kind of one dimensionality into the two-dimensional plane. Or in other words, the plane loses its identity and tries to become a line. And in fact, if I do this infinite times, I'll be just ending up with a one-dimensional object or a single line. Now, this kind of triangle is known as the Sierpinski triangle, and it has a dimensionality of 1.585. Now, let's also do this for the three-dimensional case. I have a cube. Now, what I do here is I divide each line into three equal parts and join them. And what I do right now is I remove the center cube that has been formed from each body. So it's basically like a Rubik's cube where the center piece is removed, and also the centermost piece is also removed. Now I can also do this infinite more times, where I'll be able to do. I'll have to construct. I'll have to remove this from each piece and redo this. So what I'm doing right now is I have a scaling factor of 3, and the number of pieces that have been formed will be 1, 2, 3, 4, 5, 6, 7, 8 times 2 plus 1, 2, 3, 4, which is 20. And this is obtained by 1, 2, 3, 4, 5, 6, 7, 8. Similarly, you have a backside that also gives you 8, totally 16, but the center side will have only 4 of the pieces, so we'll get 20 as the value. Now, if we take the dimensionality of this, we get log 20 to the base 3, which is 2.726. Again, what happens here is that the okay, so what happens is that if I do this infinite times, the third dimensional object will lose a sense of its identity and tries to become a two-dimensional object. Therefore, this kind of a figure is known as a Menger sponge. Now, how do we use this in the analysis of fractal dimension? It mainly comes from here, which is the Koshka and the Sierpinski triangle, where we have a circle which has a dimensionality of 1, but if you have multiple circles that are connected together to form a bigger circle, let us say that each has a radius of each form together form radius that has a diameter of, okay, let's this. Now, what is formed is a larger circle consisting of multiple circles, and let's say that the diameter of the larger circle is, let's say, 3 times the diameter of smaller circles. So in that case, although I have not written it directly, I'll be able to fit. Let me draw it a little bit more neatly. I will be able to make much more sense out of it. So if we have a circle like this, and like this, and like this, such that the diameter of uh, the entire one will be twice the diameter of the smaller ones, and I'll be able to fit a few more circles onto this. So the scaling factor could be 2, but the number of pieces that are formed will be more than that or less than that, depending on how well we are able to manage. So imagine these are spheres where each sphere is joined like this. Let's say that 7 spheres are in here. What you're gonna get is a dimensionality that will be different from n will be here less than based on how we draw, n will not be equal to 4. Suppose we have two spheres that are joined together, you get two circles. That's not possible here. Therefore, you'll get a dimensionality that is in between 1 and 2. And these kind of fractal dimensions are what is important here. So the concept of fractal dimensions which I have used explained here is used to characterize colloidal aggregates. For a 3-dimensional aggregate, we know that the volume of there will be a porous membrane associated, or there will be some voidages that are there in each aggregate. Therefore, it loses 3-dimensionality and become less than 3. The correct answer is the fractal dimension of the colloidal aggregates will be less than 3. Okay, since this is over, we'll go on to the last question, which is given by this. In a system of charge stabilized particles, the total interaction potential as a function of separation distance phi of r is given by the sum of the attractive phi of r and the repulsive of r interactions. The attractive interactions in such a colloidal system arise due to, well, is it due to surface charge, the van der Waals forces, the depletion, or the bridging? The answer is it arises due to the van der Waals forces. The surface charge provides the repulsion, and the depletion effects, depending on the concentration, may be repulsive or attractive. The bridging just generally brings particles closer together. So yeah, I think we'll be stopping here. I'll do the practice problems and the extra questions next week. Since we are running out of time, please feel free to let me know if you have any questions. And with that, I'll end the session here. I thank you for your time and attention.